Alright, welcome to my paper presentation. My name is Ryan Palmer. I will be presenting the paper Edge Friend, Fast and Deterministic Catmull-Clark Subdivision Surfaces. This is a paper by Bastian, Kuth, Max Oberberger, Matthäus, Chajdas, and Quirin, Meyer. So this was published in computer graphics form. It was presented in SIGGRAPH 23. Presented in SIGGRAPH 24, sorry. Very nice. So I will start by reviewing Catmull-Clark Subdivision. We'll go over what this paper is actually about, a little bit of compute shader, and work achieved, results, and then future work. Voila. Okay, so a bit of a quick Catmull-Clark Subdivision review. As you remember, Catmull-Clark Subdivision takes polygons, breaks them into quads, or breaks a whole mesh into a mesh of quads. So, you define centroids of each face, then you define these edge points, which are an average between two vertices of the edge and the two faces of that edge. Then you update vertex points using all of the vertices in the surrounding faces. And then you connect points with the new edges, and then you just repeat that process until it's smooth. So, some main implementation types that the paper addresses as, associated work. Three main types: patch-based subdivision, breadth-first subdivision, and direct evaluation. The one that this paper actually implements is breadth-first subdivision, but we'll talk about all three types. So, patch-based subdivision is one that you split the mesh into these patches, and then you subdivide individual patches. So you're subdividing pieces of the mesh that you want to see smoother improvements to. But this can create some really bad floating point rounding errors and can cause cracks to appear between the triangles. Breadth-first subdivision can achieve view-adaptive crack-free tessellations by subdividing the entire surface all at once, but it can be computationally complex or take up a lot of time and space. And then there's direct evaluation. Since Catmull-Clark generalizes the bicubic B-splines surfaces, you can actually use direct evaluation on these B-splines to come up with the surface. This does become problematic, though, with extraordinary vertices and strange surfaces, and other types of strange surfaces. So yes, breadth-first subdivision is the way to go here. Here is a quick video that I found from one of the authors of this paper introducing this topic.
We present Edge Friend, a data structure for fast and deterministic Catmull-Clark subdivision surfaces. We exploit that after one subdivision, two opposing edges can be uniquely and implicitly assigned to each quad by alternating the quad's rotation. The two remaining edges can be accessed via our so-called edge friends. We present a combined method for both refining edge friend and the rendering of the refined mesh. For this sample mesh, we generate and render 2.9 million triangles in less than 0.6 milliseconds. Our algorithm can be easily extended to support common Catmull-Clark subdivision features, such as semi-sharp creases or animation. We present.
So yes, as he has discussed here, there we go. Some of the work that they have achieved in this paper is they've created edge friends, which is basically a simplification of a half-edge data structure that only keeps relevant information about the subdivision process. There are some key details. We'll get to that later. They can handle semi-sharp creases, so they can crease edges so that they can, make better meshes. They can also handle boundary meshes, where the mesh isn't complete and there are holes or pieces of meshes stitched together. It's very nice. And rendering and shading. They can do some really nice things with rendering and shading, such as using the limit surface normal to find the normal direction of the actual surface that the subdivision is converging to, and provide that normal value for shading. Anyways, So how does the data structure actually work? So basically, they pre-process every corner of the mesh. So every face, they create these buckets of four vertices per degree of the face. Yeah, that should be the way to say it. So for this one triangle, they create 12 of these buckets, or I guess, yeah, because they know it's going to be divided into 3 quads, and each quad is going to reference 4 of the vertices. So this thing will get, so for instance, so if we look at this quad 1, it gets divided into, we know quad 1 has edges 1, 9, 7, 10, which you can see here, 1, 9, 7, 10, part of quad 1. The thing that they reference in the video, the on edges and off edges, are these. You can see them marked right here, these lines. Basically, each quad only tracks its 2 on edges and then tracks a pointer to the off edge. And with this pattern, every off edge happens to be the on edge of another quad. And they can tile an entire mesh like that. It just works. So for instance, we have 110 and 7, 9 being the on edges of quad 1 here. And one of our off edges is edge 5, and edge 5 is over here in quad 2 because it's an on edge of quad 2, 7, 10 right there. So with this data structure, we can store the quads, the new quads that we've broken the mesh into. We can store references to the off edges. And that's that. Here is the example they like using in the paper. You can see the on edges and the off edges zoomed in here. I will go on to my example here, so I can draw pretty much how the GPU tends to calculate these values. So the GPU, or when this data is given, the first pass does a lot of things, but what it does, it will first grab these face vertices, because the face vertices are very easy to calculate. All we're looking at are these 2 on edges that are stored right next to that face in the data structure. Because when you look at these on edges, they are storing, of course, these vertices, and that is all we need to calculate our face vertex here. So for every face, we go through and we calculate face vertex, face vertex, face vertex, right? Great. And then we're going to go through and calculate our edge vertices. For this, we're going to use our off edges. What's nice here, so we're going to start with this pink face, and we're going to look at this off edge here. With this off edge is stored within this face, and it is stored as a reference inside this face. So we have access to these 2 points, and this is an edge, so we have access to these 2 points, and voila, we can calculate our new edge points. So using these off edges. So for every face, we compute the new edge, and all this is being stored in a new buffer that we're filling up based off the our calculations this. And we can tile the entire face by calculating all these edge points. And then, a step further, we now need to calculate our vertices, our updated vertex positions. So that's a little trickier, right? We need these points, and to calculate these points, we need all of the, not all of, well, I say all of these, but realistically, we actually need these face values, and we need these edge values. But to calculate all those points, right, what we needed for that was all of these vertex positions, and these faces. And the faces are, of course, calculated from these same vertex positions. So what's really nice is, since we have a really nice symmetry right here, where you know these like rotations about here, we can just iterate over every vertex in the, or every face. And for every face, we're going to look at these three, we're going to look at these vertices, and we're going to add them all into this value. And we're going to do that at every face. And every vertex is going to get added to every single other vertex. And then you come through with a big sweep that just divides it all out. And in basically no time flat, you have calculated the new vertex positions, all kind of in the new buffer here. It's great. So, getting a move on here, because I am running low on time. I'll talk about the results. So they have a lot of meshes here. They have a mix of normal meshes, meshes with holes that need to be filled with these ghost edges and quads, and some use this like creasing, right? Anyways, so they compare times, subdivision times, from their method in blue here, with kind of like a go-to implementation using half edges. And of course you can see subdivision times going up using the same meshes, going up from the 4, 5, 6 iterations on AMD or NVIDIA. Their method just blows, their method just blows the half edge method out of the water. Same thing happens here with rendering. Rendering's a bit of a more interesting story, because I mentioned how they are storing, let me just go back. So one reason they are storing the data structure like this is so that they can interweave the information, and when this information is given to the GPU, it is all present within the same location. One problem with subdivision using half-edge data structures is typically new edges, new vertices, and such are added to the back of said data structure. So as you take more and more iterations, the memory locations of vertices spread out throughout the data structure. But what's nice here is that since it's like interwoven, every face has access precisely to the data that it needs, aside from some neighboring half edges, but those are, or some neighboring off edges, but those are also neighboring in the data structure. It's very great. So there's some really nice rendering time saves here. And yeah, for conclusions and future work, this paper really didn't have too much to say in terms of future work, but they're planning to adapt their method to subdivision based on surface flatness and distance to the camera next. Anyway, thank you for this. I went a little over time, but awesome.